Hi everyone, thanks for checking out this video. So this is going to be another lesson in this series I've been making on the topic of parameter estimation. So I think the best way to get good at parameter estimation is to just practice doing it and do it with more and more different models and stuff. So in this video, I'm going to be showing you guys how to estimate parameters for the predator-prey model. So if you guys haven't already watched my previous videos on the predator-prey model, I'm going to refer you guys to those, and I'll put the links in my description for the basics of the model and how to implement it in Python. So I'm kind of assuming that you guys have already watched those, and I'm also assuming that you guys have already watched my previous parameter estimation videos. So if you guys haven't watched those, I'll also refer you guys to those in the description. But yeah, so this video is basically trying to be more practice with parameter estimation. This time, estimating the parameters of the predator-prey model. So just to quickly review, this is a model with two differential equations. So we have our prey differential equation, which we're calling x here, and here we have the population growth term for the prey. This could be fish, for example. We might have fish as the prey and bear as the predators. That's kind of the example I've been using. So first in the prey equation, we have the population growth term, alpha times x, where alpha is just some constant growth term parameter. And then we also have the population death term, which is beta times x times y. And beta here is just some constant population death term. But notice in this death term, we also have y, which is the level of the predators, because the thing killing the prey is that they're being eaten by the predators in this model. So the death term includes both the current level of the prey as well as the current level of the predators, and then some constant parameter beta. And then for the predators, similarly, we also have this this growth term. But so we have our constant growth parameter delta, but then notice that the growth term also includes x, which is the current level of the prey. And that's because for the predator population to grow, they need to be getting enough to eat. So there has to be enough prey that the predators are getting enough food to eat so they can population can keep growing. And then we also have for the predators just some death term, which is just some constant gamma times the current level of the predators. Okay, so for this video, I've made up a practice data set. So this is just some fake data set I made up, which is some hypothetical population measures of fish and bear populations over 50 years. So it's just kind of thinking the past 50 years or so, there's been one measurement of these populations per year, and we can kind of see they kind of have this oscillating pattern that we expect with this predator-prey model. And I kind of purposely made this data set kind of nice and easy so that we should hopefully be able to fit the parameters to it and just get a nice result. But just to kind of warn you guys, when you're doing this with real data sets, it probably won't look this nice. It won't be this clean and easy to fit. So probably real life data sets could be a lot noisier. But okay, so we have this hypothetical data set, and our goal now is to fit this predator-prey model to this data set by estimating these four constant parameters. So we're trying to estimate alpha, beta, delta, and gamma, and estimate their values in a way that makes this model fit this data set as closely as possible. And I'm going to show you guys how to do that in Python. Okay, so let's get started. So the first thing we do is always just import the libraries we're going to be using. So we're going to be using matplotlib, numpy, csv, scipy.optimize, and scipy.integrate, the ODE function. I guess, yeah, first things first, I'll just show you guys the data in CSV format too. So I made this this CSV, which is just it's just all this this scatter plot data in CSV format. So we have our first column is the years, and then for each one of these years, it'll be the fish population in hundreds, and then the bear population in hundreds. So these are years since the measurements started happening. So it goes up to 50 years, 50 year monitoring of these populations. Okay, so let's just see if we can like read this data in properly and then like recreate that plot that I was showing you guys. We can just kind of start there to just kind of get this data in that we're working with. So first of all, make 3 lists just to like fill up with our data. So the first one will just be called years, and then call the second one fish pop for fish population, and then bears pop. So basically, we're going to try to read in the CSV, and just for each of these columns, we're going to fill up these empty lists with these columns of data. Okay, so going to be a little bit lazy here, and just like copy and paste the actual CSV reading in code. Just yeah, being a little bit lazy, but I'll explain what this is doing here. So this is just opening this CSV file and calling it file, and then defining our CSV reader with the delimiter being commas. If this was like a tab separated file or something, you'd want to make the delimiter like tabs, or if it was spaces, you'd make it spaces, but this is comma separated, so we're making this delimiter commas. And then we have like the first row is just the headings, so we want to skip over this first row. So we're just going to say like next reader. That's just skipping over the first row because we don't want to read in those headings. And then like what we're going to do is just iterate through all of the rows of data, and for all of them we're just going to append like the first element in the row to our years list, the second element to our fish pop list, and then the third element to our bears pop list. And very importantly, like I always tell you guys, we need to remember to cast these into floats when we're appending them, because even though, I mean, we can see in our data they look like numbers, but when you read in a CSV, if you don't specifically cast it into a specific data type, it gets read in as a string. So we need to make sure we cast it into a float, so we're getting it in like a number format that we can use. So then next, I'm just gonna like just see if we can recreate this like scatter plot I was showing you guys. So again, gonna be a little bit lazy and just like copy and paste this in. But then I'll explain like what each part is doing for you guys. So this is just defining this plot, which is going to have 2 subplots, and then we're going to make a scatter plot with our years and our fish populations and color that blue. And then we're going to in the second subplot make a scatter plot of our years and bear populations, and then color that red. And then also just trying to get a good habit of like labeling things properly. So yeah, have these labels as well. So let's just see what this looks like and see if we're like on the right track so far. So just say plt.show down here. So let's try yeah, okay, so we were able to read our data in and then plot it and recreate this plot. So it looks like we're on the right track so far, at least. So for now, I'm just going to comment out this plot, but we'll leave it here in case we need it again later. But so now what I'm going to do next is, and sorry for again kind of being lazy, but it's just all these things we've done so far have been like covered in previous videos. So I've just been kind of like copying and pasting them in and kind of quickly reviewing them. And I'm going to do that one more time just with this like actual ODE function. So this is going to be the actual ODE Python model of this predator-prey model. And if you guys haven't seen this before, if you're confused by what this is, I'm again going to refer you guys to my like previous like introductory Python video on the predator-prey ODE model. So if you guys don't know what this is, I'm just going to put the link in the description to how to write all of this and what all of this means, but also like quickly review it here too. So basically, we're just defining a function that's basically just going to be the Python function of this system of 2 ODEs here. So we're passing in some variables, which are this like x and y variable, and then we're passing in a list of the params. So we have our alpha, beta, delta, and gamma. That's just going to be passed in like in list format. So then we define our variables locally as x and y, and then we define all of our parameters locally, and then we're basically just like writing down exactly these 2 ODEs. We write them down here, and then we return them. Again in list format. So if any of that's confusing to you guys, I'm just going to refer you to my like previous Python video. kind of went through it fast here, but yeah, basically the point of this function is to allow us to run a simulation of this ODE system in Python. Okay, so now we're getting to the point where we're going to actually start to define a loss function to measure our model's loss for some set of parameters when compared to the data. So this is something that's hopefully, if you guys have been like watching my like previous parameter estimation videos, this should be kind of like a little bit of a review. But I think it's good to like do this to get more practice with like different models and stuff. So we're gonna like write this again kind of from scratch and just so you guys can like practice writing these loss functions. So we're just gonna call our function loss function, just keeping it simple, and it's gonna take as the arguments the list of the params that we're testing. So just to remind you guys, it's like the way we fit a model to data is we try out a bunch of random sets of parameters, and for every like randomly chosen set of parameters, we want to see how closely the output of the model fits our data points. And the difference between our model and the data points for some given set of parameters is what's called the loss. So we're writing this loss function to measure like how far off our model is from the data points for some like randomly chosen set of parameters that we're passing in. And the goal is to like express this like inaccuracy of the model in this loss function, and then we're just gonna like fit the parameters to the data by minimizing this loss function to see like which set of parameters leads to the least amount of loss, which means that the model will be like closest to the actual data points. So yeah, we're going to pass in our list of parameters that we're testing. Then we're going to pass in all of our like data, all of our real data, which is our years list, our fish pop list, and our bears pop list. Okay, so then now we're going to actually like, now what we need to do is within this loss function, we're going to run a simulation of the ODE system with our randomly chosen parameters that we're testing. And then we're going to compare the output of that simulation to our actual data points and then like quantify how far off the model is from our data points as our loss. So the first thing we need to do is just like figure out how to run this simulation, like running it with these parameters we're testing. So the first thing is just defining our initial condition. So the way we're going to do this is the initial condition is just going to be like our first row of data here. Our first row. This is just the definition of what an initial condition is. It's like where the model's starting point is. So it's going to be this here. It's going to be like 10.0 something something 100 fish, and then 0.78 something something 100 bears. That'll be our initial condition here. So the way we're going to do that is just making this list here with the first element of our fish pop list, and also the first element of our bears pop list. So this is just going to be like our initial condition for the ODE model is just going to be our first row of data that we have. Okay, so now we need to define some time points that we're going to solve the ODE over. So we're going to use the NumPy linspace function for this. So we're going to say np.linspace, and then we want to go from our starting time point to our ending time point. So we're going to say it's going from years, first element of this years list, and it's going to go to the last element of the years list. So this is the syntax for the last element of a list. It's the -1 index. So this is going to just say we want time points from our first year to our last year. And then we want one time point in our ODE like output for every data point we have. So we're going to say num, which is the number of time points we want. It's going to be the length of the years list. So by the way, this syntax is only going to work if your data points are like evenly spaced out. Otherwise, this is going to cause some problems. But the way I'm showing you guys in this video, it's just going to kind of assume that like your measurements are like evenly spaced out in like a nice way. But yeah, this is just saying we want an array of time points to solve over, starting from our first year going to our last year, and we want the number of time points that we're solving over to equal the number of measurements we have in our real data. Okay, so now we're ready to actually start like solving the ODEs for these parameters and initial conditions and time points that we're solving over. So for this part, we're going to say output equals ODE int. This is this ODE solver that we imported. And then the syntax here is going to be the name of our ODE function. I called it sim, but you guys can call it whatever you want. So just the name of our ODE function, our initial condition list, our time points we're solving over. And then to pass in our actual params, the syntax for that is going to be args equals parentheses, params, comma, close parentheses. So a little bit of like weird syntax there, but that's just something you can remember, or you can just copy and paste it or whatever. Okay, so this will give us like some output for this like randomly chosen set of parameters. It'll give us like output of our ODE model. And then from here, what we can do is define some loss, which will start at 0. And then we're going to go through, and then for every data point we have, we're going to compare our data point to the output of our ODE model with this set of parameters, and add to the loss based on how far off our model is from the actual data. So we're going to do this in a for loop. We're going to say for I in range len years. So basically just like iterating through all of our data points. And then we're going to say like data fish equals fish pop I. That's our actual like level of the fish population in the data. And then we're going to say model fish, equals the output of our ODE solver at time point I, and we want the first column of data for the output of this ODE solver, because that'll be the fish column. And then so that'll give us our actual level of the fish population in the data, as well as our model's predicted fish population level for that same time point. And then we're going to just copy and paste this again, and then do the same thing for the bears. And then we're going to just change this to be the second column, so column index 1, which is the bears column. So now we have for both animals, we have our actual data, like of the actual level of the population in our data set, as well as our model prediction for the set of parameters of what what the model predicts the population level would be. So now we're going to define our residual, which, remember, the residual is just what's often sometimes called the error of the model, which is just how far off our model is from the data. So we're going to say res equals the difference between the fish population level in the data and the model prediction of fish population level. And then we need to remember to square this too, because otherwise it could come up like negative or something, and that could like screw up what we're doing here. So we want it to be like positive no matter what. So we're going to square this difference here. So get the square difference, and then add that to the same thing for the bears. So just to review again what this is just defining how far off our model is with its predictions of the population levels compared to the actual population levels in the data. So we're just quantifying that, and then we're going to add this residual to our total loss. So this will just go, this for loop will just go through every data point we have and compare it to the model and define the residual for how far off the model is, and then just add that to the loss for all the data points. Okay, so now we just need to return the loss, and now we have the loss function basically complete. So this loss function, like I said, it's basically going to tell us how far off our model is from the data for some given parameter set that we're passing into it. So the goal is to minimize this loss function and see what parameter set minimizes the loss so that the model fits the data as closely as possible. So the way we're going to do this is with the SciPy fmin function. So we're going to first of all, we need to kind of like define some set of parameters we're going to start off with as a guess. So I'll call this param0 equals np.array. We're just going to start off guessing 1 for all of the parameters. I'm just kind of using this for example here. In real life, if you're working with like a real ecological data set, it might be like kind of difficult and it might be like worthwhile to try to like really figure out good starting estimates for the parameters. But for now, I'm just going to start off guessing all of them as 1, just so we have something to get started with. And then we're going to say minimum equals, and this line's a little bit long, so bear with me, but it's going to be scipy.optimize.fmin. This is going to be our function minimization function that we're going to use to minimize the loss function here. So we're going to say the name of our loss function, which I just called loss function. You guys can call it something else if you want to, but it's good to just, I think, keep it simple. And then our first guess for the parameters, param0. And then we need to pass in all of our args. So the args in this case is going to be years, the fish population list, and then the bears population list. So basically, the args we're passing in are all of our like real data that we're going to be using to compare to the model. Okay, so hopefully this will work. If this works properly, it should hopefully give us predictions for all of the parameters. So I'm just going to like try printing this out and see what it gives us. Yeah, I'll just try running this in just for now and just see. Hopefully we get some predictions for these parameters. Okay, so we got something here. So here it predicted for us, it predicted all 4 of these parameters. So it predicted 0.98 something something for alpha, 0.38 something something for beta, 0.11 something something for delta, and then 0.45 something something for gamma. So at the end of this video, I'll show you guys what parameters I actually used to generate this data, and we can see how close it got. But before we do that, I'm just going to show you guys how to plot the fit model, like plot it along with the scatter plot data to see like visually how well it fits. Okay, so to do that, we're just going to first of all just like define what our parameters are from this minimum array that we got out of this this minimization function. So we're going to say alpha fit equals minimum the first element. So basically that'll give us this first element of this this minimum array output that we got here. And then let's see, beta fit is the second element. Okay, delta fit, third element, and then gamma fit is the fourth element. Okay, so now we're gonna run our ODE simulation again using these fit parameters to see how closely they match like visually the scatter plot data. So we're just going to put all these into a params list. Okay. And then, so like we did before, just use our same initial condition. Just copy and paste this. This will be just what we're starting with here. And then, yeah, same linspace. These are going to be the time points where we're solving over. Although this time, instead of giving us one time point for each of the data points, I want to get kind of a smoother curve, so I'm going to give it more time points to solve over. I'll give it 1,000 time points in this range. And then, yeah, just copy and paste again the ODE solver here. And then to actually graph this again, I'm going to be one last time. This will be like the last time. I promise. Going to be a little bit lazy and just copy and paste in the graphing again. Just going to change these to be output. So this is going to plot these two population levels that we get out of the ODE solver. So this first line here is plotting the fish population, which is output all of the rows in the first column. That'll be our fish population levels from the ODE output. I'm plotting those over the time points. And then the second line here, same thing, except it'll be the second column in the ODE solver output, which will be our bear population. Okay, so we'll plot this. And then I'm also just gonna uncomment this stuff up here so that we can get the scatter plot too, and then kind of see both of them together, see how well they fit. Okay, so let's try running this. Okay, so it looks like the lines fit our data pretty well, which I kind of did this on purpose. I kind of made this example like some easy data where it's like really easy and nice to get a good line fit. But just to warn you guys, it's like I said, like in real life, it's probably going to be more difficult than this, and you might not get as good of a fit for your model. But just for this like practice model, I kind of gave us like a nice, easy data set to work with where we're able to get like a really nice fit out of it, just to kind of like show you guys the concept and help us get some practice with this topic of like parameter estimation. Okay, yeah. So I mean, this is what we were hoping to get. We got a nice fit for our model. Looks pretty good. So now that we're at the end of the video, I'll show you guys what parameters I actually used to generate this fake data that I made. And if you guys want to generate the data for yourself too, I'll put all this code like usual just up on my GitHub, and then you can run this code to like generate your own fake data and practice with it. So I used 1.1 for alpha, 0.4 for beta, 0.1 for delta, and then 0.4 for gamma. And then to generate the fake data, I basically just ran the ODEs with these parameters, and then I added like a little bit of noise to the results. I gave it a little bit of noise in the output. But yeah, so we can see that our predicted values were like a little bit off. I mean, it definitely wasn't perfect. They're not exactly correct, but they're like pretty close. We got like, instead of 1.1, we got like 0.98, and instead of 4, we got 0.38, and instead of just 0.1, we got 0.1 something something, and then instead of just 0.4, we got 0.4 something something. So it definitely wasn't perfect, but you know, like reasonably close. Pretty okay estimate of these parameters, I think. But yeah, so hope this was useful to you guys. Just a little bit of, like more practice with this parameter estimation. Probably gonna make a couple more videos on this parameter estimation topic using some different models. And yeah, like usual, I'll put all this code on my GitHub if you guys want to download and practice yourself. And if anyone has any questions or anything, just let me know in the comments and I'll try to answer them. But yeah, that's all I have for you guys today. So thanks for watching and see you next time.